The sun's out, bro. The sun's out.
Are you serious?
Yeah.
Yeah,
We gotta go. Let's go.
We got to.
You said it.
We got a telescope problem.
Sun's out. Guns out.
Problem.
What's the telescope problem?
Sun's out. Guns out.
The
right?
telescope
Are you serious?
is I've got the tripod is broken.
You promised.
And I've got to fix the tripod. I've been working on it, but I'm not there yet.
You promised.
So we're gonna have to wait. We're gonna do it though. I promise you.
You promised.
No.
It's your fault.
Plus, we don't have much time today because it's a short period. So we'll do it. It'll be great.
It'll be great. It'll be great.
Donald Trump. It's gonna be great.
It's gonna be huge.
Promise you.
Huge. Huge.
So these are sunspots. So you see sunspots on the surface of the sun, and although they look small on the surface of the sun is so big that if you were actually on the sun, they'd be big. Here's about the size of the Earth compared to a sunspot. And what a sunspot results from is material moving out of the sun and kind of looping up and going back down into the sun. Sunspots always come in pairs. So, and it's because the magnetic field of the sun, so the Earth has a magnetic field. If I were to draw the Earth here, eraser. Are y'all with me up here? Here's the Earth.
Well, that was a good perfect.
And I'm pretty good at circles. And the Earth has these magnetic field lines, right? That go from north to south. Y'all know about these magnetic field lines, right?
Yeah.
Yeah.
Your compasses follow this magnetic field point north. Well, the sun has a really strong magnetic field because it's got a lot of hydrogen inside it, circulating around. That's under high pressure locations, and forms liquid metallic hydrogen to some extent, although it gets quickly broken apart. But anyway, the moving hydrogen in the sun forms a strong. The sun has a really strong magnetic field, and the magnetic field lines of the sun are not only outside the sun like they are outside the Earth, they're also inside the sun. You have magnetic field lines going inside the sun. And sometimes those magnetic field lines, they pop out of the surface of the sun. And they get all tangled up, which I'm going to show you. But these lines can get all tangled up, and some can pop out of the sun like that. And where they pop out of the sun and go back into the sun, those are sunspots. Does that make sense? The magnetic field lines of the sun are not nice and straight like I've drawn here, but they're often kind of squiggly. And if the squiggle goes out of the sun and comes back into the sun, you got two sunspots right there. And the reason why is because the sun's superheated gases follow the magnetic field lines. Because they're charged particles, they're protons and electrons, and they follow this magnetic field out of the sun and back into the sun. So it's a little bit cooler there where they come out because there's not as much material on the surface. The material is further out here. Yeah.
Did you see their magnetic field was messed up because of like it's different at the poles?
I'm going to show you why the magnetic field gets messed up.
Okay.
It's the differential rotation. Remember that? The middle of the sun spins faster than the poles. Maggie, you with me?
Yes.
And so anyway, this twisted, weird magnetic field of the sun causes all these different disturbances on the surface of the sun. That's showing a video of a picture of the surface of the sun, and you can see these lines here, all this red material here, and that little curve right there. That's material coming up out of the sun, following the magnetic field as it comes up out of the sun. Sun has an intense magnetic field. Now they've been watching sunspots Actually, before that, let me show you this video. This video shows it real good about the magnetic field.
By passing a sunbeam through a triangular glass prism, Willis, Texas, gas rises through the granules, cools, and descends again through the
Okay, that's showing solar granulation. Y'all remember that? And these are sunspots. You can see, if you look at them up close, they come in pairs. See that pair there?
Mm-hmm.
And there's a pair there. And there's a pair there.
That's a big blob.
That's a big blob. That's a lot of sunspot activity. When we'll look at the sun, we'll see a couple of
Can't you have
spots.
sunspots on your body?
Yeah, that's a different type of sunspot.
Oh, wow.
Why are they called the same thing?
Well, the sunspots on your body are made by the sun burning your body. They're not
On the sun.
areas of cool gases that are rising out of your body.
We are not on the sun.
That would kind of be cool.
That would be cool. Okay, so this is showing you some sunspots up close, and sunspots look cool. And like I say, it's cooler areas of the sun. It's not actually cold areas, though. It's still about 5,000 degrees. And this is the sun. Okay, so this shows, okay, this is the magnetic field lines of the sun. Pay attention here. This is the important part to understanding. Look at these. This is the sun's magnetic field lines. They're going all over the place, coming out of the sun. But it's not always like that. So they're going to show you how the sun's magnetic field gets like that. Gorilla tape? These kids didn't believe me when I told them I was trying to fix the tripod.
He promised.
He's proof of me trying to fix a tripod. Thank you very much. I'll get it back to you.
He promised.
That's funny. I had requested that Gorilla tape 2 days ago, and I just got it when y'all were asking me. Yeah. Okay, so here we go. Let's try it again. Maybe it was yesterday I requested. But anyway, keep going.
Immediate gratification.
So watch how the sun's magnetic field gets this way. Okay, so here we are at the start of the solar cycle. And, oh wait, let me back this up. Back it up. Hold on. Here we go. This is the start of the solar cycle. So here we go. The sun is on an 11-year cycle. At the start of the solar cycle, these are the magnetic field lines. Everything is straight. Aubrey, you got to pay attention to this. This is unreal.
I'm sorry, I'm trying to finish it.
Okay, so at the start of the solar cycle, at the start of the 11-year cycle, all the magnetic field lines is straight. Did I mention the middle spins faster than the poles?
You did.
So watch what happens to the magnetic field line as the middle spins faster than the poles. The magnetic field gets stretched. This happens over 11 years. Stretched and stretched. And once that magnetic field gets stretched enough, weird things start happening.
Oh my gosh.
The magnetic field starts coming out of the sun. You remember how I said it's not straight, it's looped and stuff? Well, everywhere where you see one of those loops coming out of the sun, those are two sunspots. And this sunspot activity reaches a maximum at 11 years. And you get all these sunspots and all this crazy stuff going on. Let's see that again. So this is an 11-year
Does it create warmer weather?
cycle. No, it doesn't have anything to do with our weather. It's not hotter or anything here on Earth. It just has to do with sunspot activity. Now, it can affect our satellite transmissions. You can cause cell phone towers and stuff to go out based on sunspot activity. It doesn't affect our weather or temperature at all.
And then after, it just like resets.
So and after it resets. So it starts, this is 2 years, 3 years, 4, 5, 6, 7, 8, 9, 10, 11 years. Well, I went too fast there, but here we go. 11 years, things are crazy, and then it starts to calm back down, and it goes back. It's actually 11 years, and so let's see the sunspot activity here. So sunspot activity goes to a maximum every 11 years, and then down to a minimum, and then up to a maximum again, and then down to a minimum. This is an 11-year cycle. So it goes from very little sunspot activity, that's when all the lines are straight, to a lot of sunspot activity, that's when all this magnetic field's flying out of the sun. The last sunspot high we had was in 2012. In 2012, there was a maximum activity. So right now, we're 4 years from that, so we're getting back down to a low level. We'll be at a low in a couple more years. It's funny, when I first started teaching astronomy, we were at a low, and I didn't know it. And I ordered this nice shade for my telescope so I could look at the sun, this filter. And I put it on there, and I looked at the sun, and I saw no sunspots. And I was like, this is screwed up. Something's wrong with my shade. I didn't know, I didn't know what was going on. I told the kids, I'm like, something's screwed up. I can't see any sunspots. And then the next year, I saw one. I was like, oh, it's not the shade. It was the sun. The sun was the problem. We were at the solar minimum when there's no sunspots. Look at that. I think that was actually the year. I think that's when I looked at it. Right there was no sunspots. And I was like, what's going on? And then I came back the next year, and there were some. And then the next year, there were even more, and so forth. And so I was happy again. That's how my mood changes by year. My mood is happier when there's a lot of sunspots, so I can see them with my telescope. So when we go out there now, we're kind of going down. You can see in different years there's been, sometimes there's really high and sometimes there's low. They call this, in the 1800s, there was the Dalton minimum, where there was not much sunspot activity even at the high times. And down here in the 1600s, from 1650 to 1700, there were really very few sunspots. And they call that the Maunder minimum. And they don't know why this goes through these cycles. They don't know why sometimes there's a lot more and sometimes there's a lot less. They're still trying to figure it out. Probably has to do with the magnetic field inside the sun. And like I said before, they don't understand magnetic fields that well. Do you see what I'm saying? Do y'all feel? So, at the time when the sun is at solar maximum and all the magnetic field is flying out of the sun, you get all these weird things. One is called a solar flare. You want to see video footage of a solar flare?
Yeah.
This is when the magnetic field comes shooting out of the sun, and it takes a lot of the gases with it. And they kind of explode off the surface of the sun. Solar flare. See all this stuff kind of... Oh, there it goes. You see that explosion?
Replay.
Oh no, let's do it again. Oh wait, I went to the next one. I screwed that up.
Oh, jeez.
What am I doing? Here we go. I wish it would. Get ready, there's an explosion coming. Bam, you see it?
Yeah.
Let's try it again.
It was real noise.
There was a minor explosion. Here comes a major explosion.
It was a bit more.
You see it?
Yeah.
One more time. Solar flare. Get ready for a solar flare. See it?
Yes.
What's this, like, is that actual time speed?
No, it's sped up. But this stuff comes shooting up. When you get an explosion like that, it's kind of like this magnetic field line. You know how the magnetic field comes out and it's in a loop? Imagine that loop breaking. Imagine there's a break there, and the end comes flying out. It's like this, and it just goes, and it throws a bunch of material off the sun. That's a solar flare. We call that a solar flare. In solar flares, the material that comes flying off the sun flies through space and creates what we call the solar wind. Have you ever heard of that?
Yeah.
The solar wind is particles coming off the sun and flying through space. And sometimes the solar wind is really thick. When there's been a flare that throws stuff out, there's a lot of solar wind coming. And if that hits the Earth, we get those real bright auroras. And so if it's not hitting the Earth, we don't get real bright auroras. But that's particles from the sun getting trapped by our Earth's magnetic field and hitting our upper atmosphere, causing a lot of heat and light in the upper atmosphere. Interesting stuff? Let's see another thing, a coronal mass ejection. This is like a larger version of a flare. And it's when a whole bunch of stuff comes off the sun. Isn't that a good term? Coronal mass ejection?
Yes.
You can see it right here, look in the corner right here. See all that stuff flying off?
Yes.
It's like a real big solar flare. Look at it shooting off there. Video footage.
Is that for real?
Yeah, that's a real picture.
Oh, this is the one we was watching.
Whoa.
Oh, that's so cool. Like this and since I can do the same thing better.
Now, if you're wondering how big that is, that's like 30 times the size of the Earth. I mean, this is a huge bunch of material. Look at all that stuff.
No.
Isn't that a beautiful picture? Yeah. Watch it. Bam. Now that coronal mass ejection will travel through space, and it kind of, because it's magnetic, the particles are positive and negatively charged, it'll kind of stay together and float through space as this big blob.
So what
And if it hits the Earth, usually there's not problems, but it can interact with the Earth's magnetic field, and if it interacts with it correctly, it can cancel out the Earth's magnetic field. And if it does that, it could let a lot of harmful particles into our atmosphere. And they don't think it would kill living things, but they do think it could knock out our electrical grid, our power, because it would cause all those particles, positive and negative charged particles, would get in our wiring system, would get in the Earth's wiring system. Oh, that just went out?
Yeah.
I did that on purpose. And cause all the power to go out everywhere in the world. That could be a problem. And they estimate it would be hard to get everything back up and running, and that could be a major disaster. It's very rare that that sort of thing happens. They think the last one that happened on Earth, the last big coronal mass ejection to directly hit the Earth and interact with our electrical system, happened in the 1800s when the first wiring was put up to send telegraph messages. And all of a sudden everything got knocked out. And they didn't know why. And now they think, going back and looking at what everybody wrote, what happened, and the evidence points to that it was a big coronal mass ejection that caused all the telegraph machines to go dead for a long time. So it's something that might happen every 150, 200 years maybe. They're not exactly sure. But the coronal mass ejection has to not only come off the sun, it has to be pointed right at us. And this thing travels through space for several days. And we've been hit by them before, but usually our magnetic field saves us and just kind of guides it around the Earth. It would have to interact exactly with the Earth's magnetic field just right to cancel it out. And the odds of that are slim. Yeah.
This might be a weird question, or like not a very good question, but does the sun just like stay in the same place because, or is it still moving through space?
The sun is moving through space around our galaxy, in orbit around the center of our galaxy.
Oh, okay.
And we're moving with it, orbiting the sun.
It's moving in space.
It's moving in space. It goes around the center of our galaxy once every 250 million years. So it's on a very slow orbit around the center of our galaxy. We're going to learn about galaxies coming up in a week or so. So I'll show you how galaxies work. That's a great question. That wasn't a bad question. Here's another view of a coronal mass ejection. They've blocked out the sun so they can see the light. It's not very bright, so you couldn't see it unless you blocked out the light from the sun. But there it is. And that thing's traveling. That's not going to hit us because that's going off to the side. How about a solar prominence? See that big loop there?
Yeah.
A solar prominence is a big loop that comes out of the sun and makes a big curve, but it doesn't. If it comes off the sun completely and heads out into space, it's a coronal mass ejection. But solar prominence often just stays attached to the sun, and it's just a big loop out there, and it can come back down into the sun. And often you see those prominences grow and then go back and get smaller over a period of several months. Solar prominence video.
Wait, so don't aurora come from the lights? I mean, the flaring of the sun?
Yeah, it comes from auroras come from see the big prominence?
Solar wind, right?
Solar wind. Particles coming from the sun that hit the earth, and the magnetic field takes it to the north and south pole.
So what would it be like flying through like aurora if it's in the atmosphere?
That's a good question. If you flew through it in a plane, it would be very hot there, and I don't know if it would damage the plane or not. I don't know. That's a good question. You can probably Google it. Could an aurora damage a plane?
Wow.
Are y'all seeing these prominences? These beautiful pictures, by the way, are taken by a couple of satellites that we have floating around in space, always pointed at the sun. And they're always looking at it. And they can warn us if a solar flare or coronal mass ejection leaves the sun and is coming towards the Earth, they'll see it. Those satellites will see it and can give us a couple of days warning. Because often it takes 3 or 4 days for that coronal mass ejection to reach the Earth. They don't go at the speed of light.
So is that looking at iron right there? Is that what you're saying? Like the Fe?
I don't know what that means, Fe.
Because it said He just a second ago.
Helium, yeah.
So I was thinking
Iron.
it'd be helium, iron.
It could, I don't know. It is looking at different temperatures. The corona, the outside of the sun, is the hottest, and so that's what that was looking at. Beautiful pictures of sun exploding. All right, done enough of that.
Do other stars do that?
All stars do this, we think. Of course, we can't see any other stars up close like we can our sun, but they think all stars are pretty much the same as far as if they're the size of our sun. They kind of behave the same.
What's the biggest star we know of?
There's red supergiants that are just huge. That's like two chapters away. We'll get into all the different star sizes. It's got a number. I don't think it has a
Is it
name.
another galaxy?
What?
It's in another galaxy, right?
No, it's in our galaxy. We don't know much about stars in other galaxies because they're so far away we can't really see them. But yeah, stars get a lot bigger than our sun. Our sun will get really big too, though. Stars go through a lifetime and they expand and then blow up. Some of them do, and some just fizzle away. We'll talk about the life of a star. That's a later chapter. Look at that. That's a great picture of that prominence coming off the sun there. Big loop. And like I say, you can fit many Earths inside that loop. That's a big loop. It would be bad if somehow the Earth was right there. We would all get fried. These are called coronal holes. So this is looking at when we pointed X-ray telescopes at the sun. X-ray telescopes pick up X-rays, and as you know, X-rays only come off of really, really hot material. Do y'all remember X-rays had really small wavelengths from vibrating particles that are really hot, vibrating really fast? Are you with me, Aubrey? You seem like you're texting people. Vibrating particles really fast, hot particles will produce X-rays. Well, the only thing X-rays come off of on the surface of the sun is the corona. So an X-ray telescope gives you a good picture of the corona. That's the hair that's kind of outside the sun, the gases that are flying off the sun, following, you can see that curve there, following magnetic field lines, this corona does. But there are areas, especially when the sun is at solar maximum, at the peak of the 11-year cycle, when all the magnetic field lines are rearranged, there are big holes, open holes in the corona. That dark area there is called a coronal hole. And that's called a coronal hole. It's where there's not really any gases coming off the sun. And what we find is it's at the coronal holes where most of the solar wind comes off. So in that area there, in that open area there, what's going on? Okay, in that open area there, and that open area there, that's like an area where particles can come off the sun and fly into space pretty easily. And these areas here that are bright, that's where particles get trapped and held in the magnetic field of the sun and heated up really hot. So the corona can get really hot because that magnetic field can grab particles and shake them up and make them real hot. And the corona can get up to 3, 4, 5 million degrees. And actually the corona, this part, is way hotter than the surface of the sun. So you see the surface of the sun not giving off any X-rays because it's too cool. And the corona giving off a lot of X-rays because it can get so hot. Which is kind of an odd thing. You would think the further away you get from the sun, the cooler it would be. But that's not the case with the corona because it's that magnetic field stirring up these particles and making them vibrate.
How close could we get to the sun before it was...
Before we get too hot?
It was not good.
Not very close. That's a good question. I don't know the answer to that. But spaceships that land on Mercury, if they would melt pretty quickly if they were on the side facing the sun. Because that's 7,000 degrees. No, that's not right. They're 700 degrees Celsius. Still very hot. 700 degrees Celsius on the side of Mercury facing the sun. That's enough to melt a lot of the components that